Right. In this session, we're going to move into Chapter 6 from your textbook and talk a little bit about rational expressions. Now, to get into this, I'm going to do a little bit of a review on what exactly does it mean to be rational in math. So we'll start to talk a little bit about something you've seen before, rational numbers. So a rational number is any number that can be expressed as the ratio of two integers. I should say two non-zero integers. And typically that ratio is expressed as a fraction. So for example, 3 over 2 would be a rational number. Negative 7 over 15 would be a rational number. 0.5 would be rational because I can express it as that same ratio. I can express it as 1/2. Therefore, it would count as a rational number, just not expressed in a rational way. 0.5. 4 would count as a rational number because it could be expressed as 4 divided by 1. So these are all examples, or are all members of the rational numbers. Rationals for interest of space. Whereas things like pi, any non-terminating decimal, things like root 2, Euler's constant, for those of you who talked about that before, are not members of the rationals. And would be what we call irrational. So if I talk about a rational number as any number that can be expressed as a ratio of two non-zero integers, then by extension a rational expression is an algebraic expression written as a ratio of two expressions. And again, I should say non-zero expressions. A few examples of this. 1 over x could count as a rational expression. X minus 5 over x squared could count as a rational expression. X cubed minus 3x plus 2 over x to the fifth plus 7 would be a rational expression, and so on. So, when we say a rational expression, that's all we're talking about, a ratio of two expressions. Now, you'll notice in this case I'm saying ratio and I'm writing down fractions. It's because ratios and fractions are basically the same thing, sometimes with a slightly different way of writing them down, but they mean the same thing for our purposes. And ratio is where we come with the phrase rational as far as math is concerned. Now, any rational expression with a variable in its denominator its denominator could have non-permissible values for that variable. And the problem arises because the ratio is effectively division. Now, when I say that, where do we come up with problems in division? And there's a little hint in this in the two places that I made a correction to change things to, say, non-zero integers. Why did I change to say non-zero? Because if I divide by 0, I end up with a problem. Dividing by 0 leads to undefined statements, things that we can't really work with very well. So, if I end up with a rational expression with a variable in the denominator, there could be values of x in these cases that wouldn't make this work, that we wouldn't be able to have allowed. For instance, in the first two, 0 would be a non-permissible value for x. In this last one, that's not really pretty, and we're not going to work with much like that at this level, but the fifth root of negative 7 would be a non-permissible value for x in that case, because it would lead to a division by 0. So, I'll even clarify this a little bit more. Any value for your variable that leads to a division by 0 is a non-permissible value. And that's going to become important as we move forward and talk about equivalent rational expressions and that sort of thing. I'm going to do a couple of examples with this. First example, I am stealing off of page 312 of your book. This is example 1 from page 312. Given, well, basically says state the non-permissible values. In A, the rational expression we're given is 5t divided by 4 SR squared. Now, what leads to division by 0? If S equals 0 or R equals 0. Well, that means that S can't equal 0 and R can't equal 0. Those are the non-permissible values for this expression. Mathematically, this expression can only work if S and R don't equal 0. Moving forward, in B, my expression is 3x divided by x times 2x minus 3. This is going to lead me to problems if x equals 0 or if 2x minus 3 equals 0. This leads me to state that x can't equal 0 and x can't equal 3 halves. Effectively, solving these statements for x gives you your non-permissible values, because those tell you what would give you division by 0 here, which is the thing we can't have. And I would tend to write that a little bit more concisely and say x can't equal 0 or 3 halves. And lastly, in this example, we have this statement. If I'm looking for non-permissible values, that means I am concerned about p squared minus p minus 12 equaling 0. Hey, it's a quadratic. Who knew? So we've got two different ways we can solve the quadratic. We can either use the quadratic formula or factor this thing, and it does factor nicely, into p plus 4 times, or p minus 4 times p plus 3. And from this, in my original statement, if p was equal to 4, this portion would be 0, and the whole denominator would be 0. So p can't equal 4, or for the same reason, negative 3. And that's how we find non-permissible values in the case of rational expressions. If it is just one expression divided by another, and there's not square roots involved or anything weird like that, if it's just one expression divided by another, then you're only really concerned about where you might get division by 0. Any place you could have division by 0, those give you non-permissible values for your expression. Alright, our next little bit is going to be about simplifying rational expressions and equivalent rational expressions. So I'm going to cram in together and call simplifying rational expressions into equivalent statements. And equivalent statements and equal statements are fairly close to the same sort of thing to say. It kind of helps to think about equivalent fractions. For instance, 1/2 and 2/4 are equivalent fractions. They are in fact equal to each other. So this is what we do when we simplify rational expressions. We make it a simpler form that is still equivalent, that has the same value. And largely we're going to do this by example, and I'm going to talk my way through a few different ones and mention a few tricks and things that can happen along the way. So I'm going to dive right into example 2, which basically says simplify the following stating non-permissible values. In A, our expression is 3x minus 6 divided by 2x squared plus x minus 10. And now in simplifying, effectively what we end up doing is moving towards a point where we can cancel some things out. And a little word about cancellations here. I cannot, nor should I ever try, to cancel out these x's. Doesn't work, doesn't happen. I cannot reduce the 6 over 10 to 3 over 5 in this case. Doesn't work, can't happen. Unless your terms are all being multiplied together, you cannot just cross stuff out top and bottom. If you've got little parts here that you're adding or subtracting, no canceling. Don't do it. You have to put this thing into a fully factored form before you can start to talk about canceling and simplifying things. So, factor first. Can't stress that enough. If it can be factored, factor it. I'm using my equal sign here to denote that what I'm about to write is equivalent to what I've started with. The 3x minus 6, I can factor 3 out of the two terms on the top and write it as 3 times x minus 2. The quadratic in the denominator, 2x squared plus x minus 10. I don't want to spend a whole lot of time showing this, but because we have factored things to death at this point. But 2x squared plus x minus 10. Two things that add up to 1 and multiply negative 20 would be 2x squared plus 5x minus 4x minus 10. I could factor an x out of the first two expressions, a negative 2 out of the second ones, and end up with 2x plus 5 times x minus 2 in my denominator. Now, I have really expressed both my numerator and denominator as a grouping of things that are being multiplied together. so that I can start to think about what can cancel. But before I do that, before I cancel anything out at this point, I should think about my non-permissible values. X can't equal 2 because of this term in the denominator, and x can't equal negative 5/2 because of this term in the denominator. So then, anything that's the same top and bottom just divides to be 1. X minus 2 divided by x minus 2, that's just 1. So what I'm left with for my simplified expression is 3 over 2x plus 5. And effectively what I'm saying here is that 3x minus 6 over 2x squared plus x minus 10 is equivalent to 3 over 2x plus 5. But I have to make a caveat here. If I put 2 in for x on this expression on the right, I'm going to get 3 over 9, 1/3, which is a number, which works out. If I put 2 in this expression on the left, I'm going to get a division by 0 problem. So these two expressions are only equivalent so long as x doesn't equal negative 5/2 or 2. And that's the whole point of the non-permissible values. It's so that when you're making equivalent statements, you can say where there's exceptions to that equivalence, where they are not equivalent, in fact. These two expressions are not equivalent at x equals negative 5/2 or x equals 2, because at least one of these doesn't exist at both of those numbers. So this would be my statement of equivalence. Or in other words, this is the simplified form of that. Another example of simplifying: 1 minus t over t squared minus 1. And you're like, oh, all sorts of stuff can cancel here. 1 and 1 can cancel. T and one of the t's can cancel. That just leaves me with 1 over t. No, don't do that. I cannot stress that enough. Don't. Factor things out. The only time you can cancel things is after you've made sure everything's factored, and it's multiplications that you're canceling, not addition and subtraction. Alright, the 1 minus t is not going to factor a whole lot. But t squared minus 1 you might recognize as a difference of perfect squares, and I can factor that into t plus 1 times t minus 1. Now that I've factored my denominator, I can talk about my non-permissible values, and t can't equal plus or minus 1, because either of those would lead me to a division by 0. But now it doesn't look like there's anything I could cancel out either. But I'm going to make one more statement. Isn't 1 minus t the same as the negative of t minus 1? And when I do that, there are things I can cancel out. And again, this holds as long as t doesn't equal plus or minus 1. T minus 1 divided by t minus 1 would just be 1. Now, a lot of times, when people cancel out everything from the numerator, they think that the only thing they're left with is what's in the denominator. I have seen people write this and go on and just say, oh, that's the same as t plus 1. It is not. This thing would be the same as negative 1 over t plus 1. So my initial expression is equivalent to negative 1 over t plus 1, so long as t does not equal plus or minus 1. And in that case, I have simplified that expression again. I've taken it, I've factored it as much as I could, I determined my non-permissible values by finding where my denominator would be equal to 0. Once factored, I canceled out as much from numerator and denominator as I could by making 1s basically anytime I divide similar terms. And then I wrote my final statement of equivalence. A couple more examples. one more example. This is example 3 from page 315. And we're given a series of questions on the rational expression 16x squared minus 9y squared divided by 8x minus 6y. And in A, we're asked to, stating slightly differently, describe the non-permissible values I'm just going to describe the non-permissible values. Well, they're going to occur in PVs, occur at 8x minus 6y equals 0. If I rearrange that for x, I would get that x equals 3/4 y, or 3y over 4. Therefore, x can't equal 3/4 y, or else I would get division by 0, and that's my non-permissible value. Now, you'll notice that this is not just one value, it depends on what you've got in for x. So for instance, if I had an x value of 1, sorry, restate that. If I had a y value of 1, my x value couldn't be 3/4. And that can happen. You can have a variable dependent non-permissible value, and you can write it out in a very similar sort of way. In B, we are asked to simplify this thing. Well, for 16x squared minus 9y squared over 8x minus 6y, I will factor this thing first. You might notice once again that the top is a difference of perfect squares. So it could factor into 4x plus 3y times 4x minus 3y. In the denominator, I can factor 2 out of everything and leave me with 4x minus 3y. Once you have found the non-permissible values, I don't really find it necessary to write it down at each step along the way, but you will need to include a statement at the end. So, my first step, before I've tried to cancel things out, I factored as much as I could. I made my expressions big combinations of multiplication, and then any of the terms I'm multiplying that are the same in my numerator and denominator, I end up with division that gives me 1. So 4x minus 3y divided by 4x minus 3y would equal 1, and this expression is equivalent to 4x plus 3y over 2, so long as x does not equal 3/4 of y. And if I summarize that, I would say that 16x squared minus 9y squared over 8x minus 6y is equivalent to 4x plus 3y over 2, so long as x does not equal 3/4 of y. And lastly, at part C, we're asked to evaluate for x equals 2.6 and y equals 1.2, and show 2 ways to work this out. First, we can quickly check to make sure that we're not violating our non-permissible value. Y is 1.2, and 3/4 of y would be less than 1.2, so obviously 2.6 is not equal to 3/4 of y. So my equivalence is fine, the equivalent statement holds. So when we say evaluate, we basically mean plug the values in and work out what it means. 16x squared minus 9y squared over 8x minus 6y would be the same as, in this case, 16 times 2 times 2.6 squared minus 9 times 1.2 squared over 8 times 2.6 minus 6 times 1.2. if I work that out. I trust the calculator. But I got a nicer number than what I just worked out. Oh, my bad. 8 times 2.6 minus 6 times 1.2. And that works out to 7. Alternatively, since I know I'm not violating my non-permissible value, I could just work out 4x plus 3y over 2. Since I simplified it, it's going to be 4 times 2.6 plus 3 times 1.2 over 2. 4 2.6s are 10.4. 10.4 plus 3.6 is 14. 14 divided by 2 is 7. They can be evaluated to the same thing, which makes sense since they are equivalent statements. Okay, so if I can summarize the simplifying process, because that's what's going to come up the most. Simplifying. Step 1, factor. I cannot stress that enough. Try to factor it as much as you can, both numerator and denominator. 2, state non-permissible values. 3, simplify any division of like terms in the multiplications to 1. And notice that's happening after you have factored everything. After step 1, if it can be factored, then things should be reduced to bits of multiplication. Okay, that's about all I have to say on that. There'll be some work attached with this in the Google Classroom, and thanks for watching.